Hello, this is Mr. McMurray, and we're doing the force and motion notes, and it's Friday afternoon, 3:53, and it's about time to go home. Apparently, I recorded this earlier, but without sound, so hopefully we're doing better this time. Some of the joys of a new computer is finding things that don't work, and that's one of them. Apparently, occasionally, when I switch from my desktop to here, it turns off my sound volume. How nice. All right, now we know that. Hopefully I won't do it again. Force and motion notes. So, talking about force and motion notes, first of all, it's pretty basic, is that what is a force, okay? A force is something, no, not something the dark side of it turns into Darth Vader. That's a different thing. That's the life force of all the organisms in the universe that can be channeled for good or bad, depending on blah, blah, you get the idea. But that's Star Wars. Okay, forces in physics, we're just talking about either a push or a pull on an object, okay? So that's a pretty basic definition, but that's kind of the way force is. It's almost one of those things we kind of know what a force is, but it is very difficult to define sometimes. Okay, but it's just a push or pull exerted by one object on another. Now, if we wanted to measure a force, we would use this. Okay, this is a spring scale. We put them on the hook here, and it would pull down, and it would measure how much force something has, the weight of something basically, because it's a spring scale, so it's measuring weight. All right. However, this one also has a little plunger on the end, and so you can push it into things, and you can see how much force it takes to push something. So, don't know if they're being good or not, but they're a new kind, and I thought, hey, that sounds good, because sometimes you want to push something, not pull, and so these are nice spring scales because they will do both. So they'll be used to measure forces. Now, if you look on the spring scale, it is measured in newtons. You probably can't see that, but there we go. All right, it's newtons. This one goes up to 5 newtons, okay? And so the force we're going to measure is going to be measured in newtons. Why newtons? Because Sir Isaac Newton explained the most, say basic of forces, but most overwhelming of forces around Earth we think of is gravity. He discovered gravity. He explained it. Now, I say he discovered it. He didn't discover it. It was already there. Things have always fallen down. But he explained gravity, which is, like I said, one of the major forces on Earth. And so they said, in honor of that, we're going to name the unit for force the Newton. Now, I've seen it with capital letters most of the time, because it is a guy's name. But sometimes since it's a unit, they'll put it in little letters. But the symbol is always a capital N. All right? So it is always going to be measured in newtons. All right? Now, if there's more than one force acting on an object, then it has what we call a net force. The net force is the result of 2 or more forces acting on an object at the same time. Okay, it's kind of like my salary. I have a gross salary, which is you take how much I get paid a year, divide it by 12, and that's how much I should get paid every month. But the actual paycheck that comes home is only about half of that. Why? Because, well, they've withdrawn insurance, retirement, my retirement fund that I put stuff into, and whatever. All these various things, they've taken money out of it. And so my net salary is about half of what my gross or total salary is. And so that's the same way with forces. With forces, you may have 2 different forces, okay, and you only get the leftover between the 2. Or, unlike my salary, they can add together and make more, okay? If I could find people to add money to my net salary, then I could make more money. Unfortunately, I'm not having a lot of luck doing that. If you're interested in donating to my salary, I will leave a phone number at the end of the video, and you can call me. All right, but generally, my net salary tends to be withdrawing things, not adding things. All right. So, what else? Well, if 2 forces are in the same direction and they're both hitting the same direction on something, then they are going to go be added together. So, for example, if we have a ball here and we put 3 newtons of force on that ball, and someone else hits it and puts 2 newtons of force in the same direction, there would be a total of 5 newtons of force on the ball, okay? So it's going to go farther and faster, and because it's getting twice as much force put on it. So if they're in the same direction, then we simply add them together. If they're in opposite directions, they are subtracted. So, for example, if we had those 2 pushing 5 newtons that way, and we put a force of 5 newtons this direction, opposite direction, they're going to subtract. And if we subtract those, we're going to get a total of 0, okay? Now, say we did this with a force of 6. Now 6 minus 5 gives you 1, so the net force would be a net force of 1 Newton, and it's always going to be in the direction of the bigger number. Okay, so it's going to be 1 Newton to the left because that's the direction of the bigger force. Okay, and so that's how we would do that if they're in opposite directions, as opposed to one direction, which is a band. You can fill in the blank whether it's a good band or a bad band. I don't know. Anyhow, so moving on. Now, if they are balanced forces, that would be like when we had the 5 Newton force down here. Okay, so we had a 5 Newton force, and we have 5 newtons that direction. They're going to cancel each other out, and so we say that they are balanced forces. And that is certainly one example. If we have equal but opposite forces, they are going to be balanced, okay, because they'll have a net force of 0. However, if I have a ball, a bowling ball, I would show you in person, but you know, I can't figure out how to get the video there, and it's rolling this direction. If I put a force of 1 Newton on the ball this way and 1 Newton on the ball this way, as it's rolling along, what's going to happen to its motion? And the answer is nothing. It's going to keep going straight down the line down here, just like it is now. It's just going to keep on going at the same speed because these two are balances. They have a net force of 0. They are not going to change the motion. Okay, and here's the key thing. Balanced forces have a net force of 0. That does not mean that the object is still. It can be. If an object is sitting still, then the forces are obviously balanced on it because it's not going anywhere, it's not changing. But if an object is already moving, it's going to keep moving exactly the same way if you put these two balanced forces on the side of the bowling ball. Why? Because net force of 0 means there is no change in the motion of the object. So if they're going straight, it's just going to keep on going straight. All right? So that's a very important thing. Net force of 0 just means there is no change in the motion of the object. If it's already moving, it'll keep moving. If it's not moving, then it'll stay not moving. It's not going to change. All right? That's a very important point. Now, if there are unbalanced forces, okay, these are forces that have a net force that is not equal to 0. Now, it says greater than 0, okay, because you can't put less than 0 force on something. But keep in mind, we could have a negative force. If this 5 newtons this direction was a positive, then since these are going in the opposite direction, we would say that they are negative. Not because they're less than 0, but because they're going in the opposite direction. Okay, so unbalanced forces have a net force greater than 0, and they are going to always result in a change. Because remember, net force is 0, no change. A net force different than 0, and there is going to be a change in the velocity. Velocity, remember, is speed, speeding up, slowing down, and direction. So if it slows up, speeds up, slows down, or changes direction, then you have a change in velocity. And if you remember, a change in velocity is called acceleration, okay? And so unbalanced forces will always cause acceleration of one sort or another. For example, down here, if I did not do this side, I just pushed, as the ball is rolling, and I only push on this side, there's nothing to balance it, and so it is going to possibly change the speed, but definitely going to change the direction of the ball, as it's going to go off more this direction now. All right, now we could draw vectors and find out exactly where it would go, but not right now, okay? All right. Now, if an object is sitting still on my counter, that means it has obviously a net force of 0, correct? All right, that means there are balanced forces on it. We know gravity is pulling it down, but it's not going down through my desk, so apparently, right, say I have the muddy bottle of water, it's not going down, so apparently there's a force on the surface that is pushing back up against it, okay, and it's canceling out the force of gravity, so the net force is 0 and it doesn't go anywhere, okay? Now, that force is called the normal force, not because it's as normal as in not weird, okay, although technically I guess it's not weird, okay, but normal in geometry, so they tell me, I'm not a geometry teacher, but normal means perpendicular to. So if something's going straight up in the air, it's perpendicular to the surface, okay? And that's why the normal force is called the normal force. And the symbol for that is an F for force, and then a capital N to show we're talking about the normal force. It's the force that a surface exerts on an object resting on it, all right? And so it's pushing up, and it is always perpendicular to the surface. So it's going straight up at a perpendicular angle compared to the surface, and it is going away from the surface, not going down into the surface. It's going away from it. That's why it pushes up on the bottle and gravity pushes down, and they cancel each other out, and we have a net force of 0. Okay, so that is the normal force. All right, now if I were to take this bottle and put it on a slanted surface, let me see if I can draw this. Let me find my pen. Okay, now it's on a slanted surface. Okay, if this is my bottle, I don't know how good a bottle I can draw, but with this, okay, close enough. This is my bottle. The normal force is still going to push this direction. It's perpendicular. Sorry, my thing stuck. It is perpendicular to the surface, so it's still going to go out this direction. But gravity is still pushing straight down. Okay? Now, since this force is going that way, we learned from vectors that it could go this, it has a horizontal force, and then it has a vertical force. Okay? And as it gets tilted, this side of the triangle, the vertical part of the force gets smaller and smaller. Well, gravity stays the same. How can it stay there? Well, as long as there's enough friction, which also has a vertical and a horizontal force to it, it can still stay there. But eventually, the vertical force of the normal force is going to get tilted so much to the side, and it's going to be so much less than the gravity that the friction is not going to be enough to make up the difference, and it's going to slide off and break, okay? So remember, it's always perpendicular to the surface, so if the surface is not flat, then it's still going to be perpendicular to the surface and go off at this angle. And that's why things start to slide when you start putting them on a slope. All right, I'm sure you've sat awake nights wondering about that, and now you know. All right. So we're going to do one more note, and then we'll stop right here. I think it's where I stopped last time. I can't remember. But here we go. Contact forces. Forces that touch an object to exert a force. Most of the time, this is what we think about. If I slap somebody, it's a contact force. I had to contact there again to exert the force, okay? Most forces we think about are contact forces, okay? We would call those, most of those would be in this category, applied forces, okay? We have to apply them. One thing hits another. A boxer hits the other boxer. A bat hits the ball. A tennis racket hits the tennis ball. A bowling ball hits the pins. All these sort of things have to be applied, okay? Some other things that exist when things touch each other is friction. Two surfaces rub against each other. They have to be in contact, and you have friction. Air resistance, as my hand moves through the air, it hits the air molecules, touches the air molecules, and you have contact with them, and so you have air resistance, okay? That is also a contact force. All right, so obviously if there are contact forces, then there are forces that are not in contact, or non-contact forces, or sometimes we call them long-range forces. Okay, these are forces that can exert themselves without actually touching an object. And an example of that would be, hang on if I get these apart. All right, these magnets. All right, I can push this magnet close to this one, and it will make the other hand bounce away. Why? Because they're exerting a force on each other. They're repelling. If I turn it around, now they pull themselves together. Even before they start touching, you can start feeling somewhere in here that, boom, all of a sudden it starts pulling them together very close. Okay, and then you got to get your fingers out of the way so it does not pinch them in there. Okay, so these are forces that are exerted without touching it. Okay, besides magnetism, there's also gravity. The moon and the earth have a gravitational pull on each other, although they're however many miles apart, hundreds of thousands of miles apart. Okay, and electricity can also do this. Electrical charges can also be attracted across a distance. And so those are non-contact forces. All right, hopefully if you watched the first one, you'll come back and watch this one and hear the exciting, thrilling lecture that goes along with it. All right, So I'm going to stop right there and call it a weekend, and have a good weekend, and hopefully we'll see you on Monday. Or at least hear from you anyhow.